Okay, so let's start the afternoon session. The first speaker is Professor Hiroshige Shiga, and he'll speak on the moduli space of Cantor sets. Please start.
Thank you. Thank you for the introduction. So first of all, I thank the organizers for inviting me to this wonderful conferences. Actually, this time is the third visit to India and the second visit to Bengaluru. So I'm happy here. So I talk about modular space of Cantor sets. So it is, we consider the quasiconformal deformation of Cantor set, the plane. So what the Cantor set? So Cantor set is denoted by E. It is a compact and totally disconnected perfect set. So in the complex plane. So totally disconnected means each point has its own connected component, and perfect set means each point is accumulation point of the set. So there are several examples of the such kind of Cantor set. So it's the most famous one is a so-called middle one-third Cantor set in the intervals. I think most of people knows the set well, but first I give you some exact construction of the Cantor set, such Cantor set C0. So because of our later use, so first of all, I take the unit interval from 0 to 1, closed interval, and we divided this interval into three sub-intervals with the same length. So should be something like that. So that is not correct picture, but so those three intervals have the same length. Maybe the length is 1/3, and the middle one is an open interval. So I remove this middle open interval. Then we have two closed interval. So we denote by this set E1. So E1 consists of two closed intervals, right? And we do the same process for each two intervals. Namely, we divided this interval, those intervals into three intervals with the same length. So, and take the middle open interval from each two intervals. So we get four closed intervals with the same length. So we denote by E2. So of course E2 is a subset of E1, right? And is a closed subset. And we make this process infinite many times. Then we take intersection of all of En. Then which is denoted by C0. So this is a Cantor set. I mean, it's a closed compact set and totally disconnected and perfect. You can check them. Okay. So next example is the limit set of the Schottky group. Okay. Okay. What is that? So maybe most of people know the definition of such group, but for the later use, I explain the definitions. So let Z is a Schottky group of rank G. So G is is an integer greater than or equal to 2. That means we have first we take a pair of circles, G pairs of circles, says that it is C1 and C2, and so C2G minus 1 to the C2G, and we take a loxodromic element, Mebel's transformation, which is loxodromic, which it sends outside of the circle of C1, it maps to the inside of C2. And so we denote by, so then gamma 1. And so likewise, we take gamma G, which sends outside of the circle C2G minus 1 into the inside of C2G. And so the sorted group G is just generated by this gamma 1 to dot gamma 2G, gamma G. So it is a free group of rank G, and the limit set, you can see the limit set is still a Cantor set. By lambda G is the limit set for G. Basically, the definition of the limit set is the same as the previous talk. So it's, you can consider the orbit of the you take at some point in somewhere, and consider the orbit of the point by G. Then it has an accumulation point. Then it is the limits of G. So you will see that this construction is a two-dimensional version of the first ones. So the first example, you have a one-dimensional segment and take some open set, and this procedure infinite many times. And the second example also the same. So you have a Riemann sphere and consider the some closed set from the, so that is a fundamental region of the group, but you can remove this open set infinite many times, then you can get the rest is the limit set of G. And the third example is a rational function, some Julia set of the rational functions. Okay. It comes from the complex dynamics, and so if you consider that RZ is rational functions of degree D is greater than or equal to 2, then you can consider the iteration of the of function. So they say we denote by R to N to Z, that's the iteration of R of N times. And look at the behavior of the iterations. I mean, if you take a Z in the Riemann sphere, and so there are some neighborhoods that such that this family of iteration is normal family, then the points belong to the so-called Fatou set. And the rest of the Fatou set is some so-called Julia set. And so Julia set of R. Sometimes R becomes a Cantor set, not always. So here we consider a rational function degree R, degree D, and the case where the Julia set is some Cantor set. And we consider the quasiconformal equivalence of the limit set, Cantor sets. So we take two Cantor sets, E1 and E2, and we say that those Cantor sets are quasiconformal equivalent if and only if there exists quasiconformal mapping phi, which is defined on the complex plane, such that it sends E1 to the E2. Okay, we do not buy E1 equivalent to QC E2. So we were interested in such kind of things because one thing is it's similar to the definition of the Teichmüller space over the moduli space, and also if you consider the complement of the Cantor set, so it's the corrected open set, and it is a Riemann surface of infinite, topologically infinite type. So in general, analysis of a Riemann surface topological infinite type is at somehow different from the compactness of a Riemann surface of finite type, and also the structure of Teichmüller space is slightly different, sometimes different from the structure of the Teichmüller space of compact Riemann surfaces. So considering such kind of things, it's important to show the quasiconformal equivalence or analysis of the quasiconformal geometry. Okay. So the main problem is here is find the conditions for two given Cantor sets to be a quasiconformal equivalent. That's the main problem. Talk. So here's here's the problem talk. First of all, I show you some result on quasiconformal maps and Riemann subset. It's a kind of a general theory, general result. And the second, we consider the dynamic, so-called dynamical Cantor sets. It's a Cantor set like given by some Kleinian group or dynamics of rational functions. And the third one is a generalized Cantor set and their modular spaces. Generalized Cantor set means I will define it later, but we show the possible. We show the construction of the middle one third Cantor set. Generalized Cantor set means I slightly modified the construction of the standard Cantor set. So that's a generalized one. And finally, we explain some recent my works. That is, I give such kind of modular spaces to some ergodic aspects. So, okay. First, I will use two lemmas for quasiconformal mapping on Riemann surfaces. The first one is the following. So let me expand by this figure. So we consider the two Riemann surfaces, R1 and R2, like this, and Jordan curves alpha1 and alpha2 each surfaces, which divided surfaces into two parts, so left and right, like this. And the assumption is there exists a quasiconformal mapping from the left side of the R1 to the right side of R2, and also right-hand side of R1 to the right-hand side of R2. So we denoted by each one phi 1 and phi 2. And the conclusion is, so there's no assumption that, so alpha 1 and alpha 2 are Jordan curves. So phi 1, it is known that phi 1 has, and phi both quasiconformal mapping has a boundary value at phi 1. But I don't need any assumption about the boundary value. I mean, they are not, they may not be different. And also, we don't assume that the Jordan curve alpha 1, I mean, maybe it may not be the smooth, or maybe the length might be the infinity. But I don't care of such kind of things. Anyway, there are the existence of such, I only assume that existence of such quasiconformal mapping. And the conclusion is then we can take a global quasiconformal mapping from the left R1 to the R2. So we can group this phi 1 and phi 2 near the Jordan curve alpha 1. So maybe experts of quasiconformal mapping believe such kind of things, but I give a rigorous proof of this lemma. And the second one is it is kind of a condition for the quasiconformal equivalence. So I'll give you some conclusion of that. So the main conclusion is the second lemma. So we consider homeomorphic Riemann surfaces, R1 and R2, we consider such surfaces. And they are of finite genus, right? Then, so we assume that QC equivalence near ideal boundary. That means there are some compact subset of R1 and R2 such that the outside of a compact subset, they are the quasiconformal equivalent. That's the condition. So here's a R1 and R2. It might be the infinity. No, genus is finite. Sorry, genus is finite. So the same genus. But it has infinite many ends. So the assumption is that there's some compact subset K1 and some compact subset K2, and there exists a quasiconformal mapping from outside of the K1 outside of K2. Then the conclusion is both Riemann surfaces are quasiconformal equivalent. That means that there is a quasiconformal mapping from whole R1 to the whole R2. But we assume that the Riemann surface is of finite genus. I assume that because we have a counterexample if the genus is infinite and still there is a homeomorphic, and there is some compact subset outside the compact subset, and there is a quasiconformal equivalent, but they are not quasiconformal equivalent. So we can construct some counterexample. So we need their Riemann surface of finite genus. Okay, so we consider dynamical constant set. So let RZ be the rational function of degree D, which D is greater than or equal to. The degrees means, so rational function is quotient by the two polynomials P and Q, and degree is maximum of the two polynomials, degree of P and degree of Q is the maximum, is the degree of the rational function R. And Fatu set is ordered by FR is I explained, as I explained, so that is a set in the complex Riemann sphere such that there exist some neighborhoods such that in the neighborhood this iteration is a normal family. And Julia set is a complement of the Fatu set. And yeah, we skipped it sometimes. We call that rational function is RZ is hyperbolic if the every critical point, if critical point means derivative, the point where the derivative vanishes, every critical point eventually belong to the some set. We call the attractive Bayesian of the rational functions, but it doesn't matter about this definition. Anyway, we can define the hyperbolic rational functions. For example, typical example is that D plus C, D is greater than 2, and C is sufficiently large, then this rational, actually the polynomial, it is a hyperbolic polynomial, and also, and the Julia set is a Cantor set. And JR is a Cantor set. Okay. And here's the first term. So if the RZ is the hyperbolic and the Julia set is the Cantor set, then the Cantor set, the Julia set of J of R, and also lambda G is a Schottky group. And so the limits of Schottky group is they are equivalent to the Caesar. Caesar is the 1,000 standard Cantor sets, as I explained. That's the first result. So it note that it depends on, so it does not depend on the rank of the Schottky group. No? So if you take rank maybe 4 Schottky group and or maybe rank 100 Schottky group, then we can get a lot of two limits, but it's a Cantor set anyway. So they are the Cauchy-Common equivalents. That's the result. But there's another Cantor set, dynamical Cantor set. We consider the Schottky group, Schottky type group, and which has rank 1 parabolic. Yeah? What is rank 1 parabolic? So in the construction of Schottky group, we have two disjoint, a pair of disjoint circles. Right? Schottky type group is rank 1 means one of sum of a circle is a tangency to each other, like this. And this tangent point is a parabolic fixed point of in this case, gamma 1. This is the Schottky type group of the with rank 1 parabolic. So my second theorem says if the Schottky type group has a rank 1 parabolic, then the limit set is not Cantor equivalent to the standard Cantor set. So of course, from theorem 1, and this limit set is not Cantor equivalent to the Schottky group, the limit set of Schottky group. Recently, Ruben Hidari shows that he extends, he generalizes this result, saying that he considers also a Schottky type group and consider the signature of the such kind of group, alpha and beta and gamma 1. The alpha 1 means so it shows the number of the generators of the group. So alpha 1 means the number of loxodromic generators. The beta I means number of rank 1 parabolic. The gamma I means rank 2 parabolic. So his the first statement 1 is so beta 1, beta and gamma is 0, both that means a short group. Then both groups are classically equivalent. That is our first theorem. And the second one is so if you have a rank 1 parabolic, but it does not have a rank 2 parabolic, then both groups are classically the limit set of both groups are classically equivalent. The third one is if they have the rank 2 parabolic and it does not have a rank 1 parabolic, then it also both groups are the same classical equivalent. And also the fourth one is the two groups has both rank 1 parabolic and rank 2 parabolics, then the limit set as classical equivalent. Okay, so yeah, now I will explain the general Cantor set and moduli spaces. First of all, we take omega, which is a sequence of the 0, 1, open 0, 1, infinite product of 0, open 0, 1 intervals, denoted by Qn. So from omega, we can consider the we can define the Cantor set E omega, which we call it a general Cantor set omega. So definition, a construction is almost the same as construction of the standard ones. I'll explain. So the starting point is the same. So we take closed interval 0, 1. So omega is given by Qn, and equal 1 to the infinity. And the first step we take, we also the same. We divided this closed interval into three sub-intervals, but lengths are different. I mean, quotient is different. So I consider the interval, middle interval, and left and right. Picture is the same, but the length of this interval is Q1. So that means rest of this 1 minus 1 divided by 2. Maybe. That's the first step. And second step we use, so the first step we use Q1, right? At the second step we use Q2. So how do I use it? So the procedure is the same. So we consider the two closed interval left and right. We divided the two intervals into 3 parts, and to remove the middle one. But the ratio is middle one is Q2. Q2. So the length of, so here is I1, here is I2. So the length of here is length of I1 times Q2. Same. Okay. The left and right interval are still the same length. We continue this process infinitely many times. Then finally, we get a Cantor set, which is my E omega. So that is intersection all of such small intervals. So you can check that this E omega is actually the Cantor set. That means are totally disconnected and perfect set. Okay. So in other words, for each element of this in the product of the one intervals, and we can get various so many Cantor sets. And standard one is standard one-third Cantor set is because it corresponds to this omega 0, which is a sequence, a constant sequence of 1/3. And yeah. And we said that so this sequence has a delta upper bound. Delta is some number between 0 and 1, or lower bound if the Qn is less than delta or greater than delta. So the first theorem about the Quasiconformal equivalence of this Cantor set is the following. So if we take two sequences omega and omega tilde, and they have a lower bounds. So it does not move to the 0. Then if this kind of number is finite, then both Cantor sets are Quasiconformal equivalent. And especially if this quantity converts to 0, then two Cantor sets asymptotically conformal. Asymptotically conformal means so it's almost conformal near the Cantor sets. And therefore, in particular, because of the asymptotically conformality, we can conclude that the Hausdorff dimension of those Cantor sets are the same. So for each omega, so which makes a Cantor set, we define the moduli space of omega. That is a sequence of omega prime such that both Cantor set as quasiconformal equivalent. So E omega prime is quasiconformal equivalent to E omega. So that is subset of this this infinite dimensional space, but we are interested in the structure of this moduli spaces. And so this theorem 3 gives sufficient conditions for omega tilde to belong to the moduli space of omega, right? So first of all, so the next I will consider the condition, necessary and sufficient condition of the sequence omega to belong to the moduli space of standard Cantor set. No? Because okay. So I will give you these conditions. So I will express that it is important is the following condition is a necessary and sufficient condition. To define this one, some strange numbers. So we consider the omega, the sequence omega, and take epsilon between 0 and 1. And we define the omega epsilon I is a natural number by the infimum of this number. That this means, so we consider qi plus k. So this is a sequence after qi, and we consider first number k, first step k, such that qi plus k is greater than or epsilon. That's the number omega epsilon I. And we define n omega epsilon by the supremum of omega epsilon I. So here I is the natural number. So here's a picture. So we have qi here, and qi plus h1 here, and epsilon, this red line is epsilon. So we look at the first step, which exceeds this red line. That's omega epsilon I. We consider the supremum of this number, then it is n of omega epsilon. So for example, so if Qn tends to some number, say Q is open interval between 0 and 1, then of course n omega epsilon is finite for some epsilon. It's much easy. Or if Qn compared to 0, then this omega epsilon is infinite for any epsilon. Because so for any epsilon, eventually Qn below the red number for any epsilon. So there's no such supremum. Okay. So the conclusion is the following. This is the theorem 4. Consider the the sequence omega belong to the moduli space of standard Cantor set if and only if, and it is upper bound is the supremum Qn is less than 1, and and this n omega epsilon is finite. That's the conclusions. This one and this one. So, yeah. Okay. To show this, we use some result about the quasiconformality of the standard middle one Cantor set. It said it is uniformly perfect and uniformly bounded. So I'll check the condition from this our conditions. It's not easy thing, so I skip the details. Okay, so from this result, so this result means we completely determine the modular space of the standard middle one Cantor set. I mean, if you have some sequence, then we can decide it belongs to the modular space of M omega 0 or not. So we generalize this or similar things and sequence which has a upper bound. So we derive by omega b with a sequence which has an upper bound. So that means that there's some constant delta, so such that Qn is less than some 1 minus delta. Delta. So that means Qn is some delta. That depends on n and for every n. Yeah. So I'll explain. So our interest is the structure of the moduli spaces, but here I consider the volume of the moduli space. Volume means the modular space is a subset of the infinitely direct product infinitely many zero product zero intervals. So this modular space is subset of omega. But this space is the product of the standard interval. So it has a Rubik measure. And we consider the infinite product of this space. Then this whole space defines a product measure from the standard Rubik measure without by infinity. So it's a infinite product of the Rubik measure. So it's a probability measure. So we consider the volume of the modular space of standard this M infinity. So first of all, we consider the modular space of omega, which is which has an upper bound. So take a sequence which has an upper bound and consider look at the Cantor set provided by this omega. Then we we may show that it is not correct proper statement. So we may show also that is injectivity radius of the complement. So the proposition 2 shows that the sequence omega is contained in the capital omega B if and only if you consider the injectivity radius of the complement of the Cantor set, then it is the injectivity radius positive. That's a condition. So what is the injectivity radius is if you consider simple closed geodesic. So the complement is opening mass of infinite type, so it is hyperbolic. So we have a hyperbolic metric, and injectivity radius means take a simple closed curve, simple closed geodesic, and then consider length and the infimum of the length for all simple closed geodesic. So that is the definition of injectivity radius of omega. That is the injectivity radius of open mass of the complement of the Cantor set. Okay. So if it is the radius is positive, then omega belongs to the capital omega B, and omega belongs to the capital omega B, then the radius is positive. It's a quite a simple concept. The proof is rather simple because suppose that. So so I will sketch the proof then, or ideal proof. So suppose that Qn tends to 1, so it does not belong to the omega B. That means, as I said before, the Qn is a portion of the removed interval. So Qn tends to 1 means quite small parts remains, right? Here's a Qn. So this part is pretty small. Okay? So you can find from this picture, you can find the annuli, something like big, which has a large modulus. Because Qn is very close to 1, big. So this part is something like this. So it's a long annulus. So it means the length of the curve is pretty short. So the omega does not have an upper bound, then the injectivity radius is close to 0. So other direction is also similar, proved by the similar considerations. Okay. Anyway, and so the positivity of injectivity radius is quasiconformal invariant. Okay. So that it's a general theory, but so take a Riemann surface, and R prime also Riemann surface. And if injectivity radius of R is positive, no, sorry, yeah. And so R and R prime Kashikawa equivalent, then injectivity radius R prime is also positive. So the proof is done by using the so-called Wolpert's lemma about the hyperbolic lengths and Kashikawa mappings. So because of this result, if omega is capital omega b, then m omega is also a subset of capital omega b, because some Kashikawa invariance of the positivity of the injectivity radius. And thus, therefore, the volume of omega, m omega, is 0. Because of this, this capital omega b, the volume of capital omega b is 0. So the subset is also measure 0. So in particular, the volume of standard one-third quantum set, modular one standard quantum set is also 0. So finally, I'll explain some ergodic consideration on this set. So as I denoted, M0, M infinity is a standard product measure in the space. And the conjecture is the following. So we show that if this omega has a bounded upper bound, then the volume of modular space is 0. The conjecture is true for any omega. That means here's a picture. So the total space is 0, the product of the unit product of 0, 1. And so the conjecture is like this, picture is like this. So that means, so here's a standard, modest standard quantum set. So so it's the measure 0, so it's a very thin, right? So we show that omega has an upper bound, then is also same. But it's also true for any other ones. That's the conjecture. And to prove this conjecture, we use some ergodic theory, right? So, you may know that ergodic theory is super measure theory. I mean, the ergodic theory deal with measure of set and measure of functions and map. So to use the ergodic theory, everything has measurable. So first of all, so we have to show that our modular space is measurable, right? So how do I prove this one? So this proposition is for any omega, the modular space is actually the F sigma set. F sigma set means countable union with a closed subset. So of course it is a polar measurable set. I will sketch the proof. So we consider we take some omega here, any omega, fix it. And we consider function f omega for which is defined by the capital K omega prime if omega prime is in the modular space. Otherwise, the plus infinity. What is this quantity? It is a maximal dilatation of extremal classical mapping from E omega to E omega prime. So omega prime. So if omega prime is belong to the modular space of omega, then there exists a classical mapping from E omega to E omega prime. We consider external classical mapping. That means minimal it has a minimal dilatation with such kind of classical mapping. There are a lot of the classical mapping not unique. So we take extremal, meaning the maximum dilatation is infinite. It exists, and so this if omega is a function. Of the space to the one to infinity, and we can show that this function is lower semi-continuous. It is shown by using some normal family argument of the classical mapping and Carl-Theodor's Cantor's theorem. But anyway, you can show that this is lower semi-continuous. And so this is the, of course, measurable functions. Right? And this, our modular space is inverse image of this, inverse image of the interval 1 to the infinity, F omega, by definition. So it must be the measurable set. Okay, so we can use the ergodic theory to the space of the modular space. We consider the so-called Bernoulli shift, or just a left shift, or simply shift. That is a map from the space to itself. That shows that it means it forgets the first element, first entries. Say, so if you have a Qn, the sequence Qn, the image of sigma is the first entry, the Q2. So it is Qn plus 1. So it is known from the ergodic theory that this mapping is measure preserving. That is this meaning, and also the action is ergodic. That is, it is invariant. Then the measure is 0 or 1. Where capital A is some measurable set. Okay, so I have not much time. So first we analyze action of the sigma on our Cantor set. First of all, we show that the image of the shift quasiconformal equivalent, then premise to say the omega 1 as also QC equivalent. We can prove this theorem by using the lemma 2. So the first, given the first section. And so it's not final conclusion, but it's a little bit improved a little bit. And so the final statement is almost, so far we can say that only this kind of things, almost measurable, almost modular space measure zero, except for one, at most one. It's a conclusion of the theory. So we stop here. Thank you.
Thank you very much. Any questions or comments, please?
Anti-classification result for Schottky group. So a Schottky group with a parabolic is not equivalent to the standard middle thirds. Yeah. Do you know anything about what happens for rational maps where you have a parabolic point on the Julia set, but it's a Cantor set?
Yeah, it's a problem, still problem. Yeah, I don't have any idea. Actually, improving the such Schottky group's case, we use somehow some strange techniques. I use the potential theory. Yeah, I consider the so-called Martin compactation of the Riemann surface and the structure of the Martin compactation of the limits quite different. So we conclude that they are not quasi-concave. The same technique cannot use rational functions. Yeah, so I have no idea.
Okay, thank you. Any other questions or comments? So you mentioned that you're kind of using a hyperbolic metric, uniformizing the complements of the sets. Do you any geometric features of that hyperbolic surface? I mean, for example, the standard Cantor set.
Yeah. Yeah, actually, it's not hyperbolic related to hyperbolic structure, but in improving this theorem, we use so-called uniform domains. It's a different categories, but it's some class of the prime domains. So if you know the John domain or something like that, then it's a kind of John domain. So it's depends. It's a little bit difficult one. So.
Okay, thank you. Any other questions or comments? Okay. Okay, well, let's thank the speaker again. Thank you.
Thank you.